Hi, my name is Charlie Kawasaki, and I'm the project rep for the research presented here. Our project is to create a fire-resistant roofing layer consisting of superabsorbent polymer and an integrated sprinkler system. As you all know, climate change is beginning to ravage our Earth, and will only continue to get worse. In both 2017 and 2018, California wildfires cost over 10,000 structures and over $13 billion in damages each of those years. One key way to help prevent this is to increase the fire resistance of the houses in wildfire-prone areas. It's important to focus on the roof and gutters, which, if caught fire, can collapse inward and burn the home completely. Class A roofs provide some protection, but not enough. The objective of this project is to design a roofing layer to be used as an emergency method to combat wildfires and minimize building damage. The primary material used here is superabsorbent polymer, or SAP. SAP can quickly absorb over 100 times its weight in water and remain a gel. It absorbs water within its matrix, restricting convective heat transfer and drastically slowing temperature increases, giving it unique fire-fighting properties. It is already used in the field to fight fires, but is not implemented in roofing structures. A typical roof has a few outer layers, including a roof deck, which is usually made of wooden boards, a waterproofing barrier, and an outer layer, which is usually metal panels or shingles. We are proposing to add another layer into this, shown in an early sketch on the right. It is a 1.5-inch layer of airspace with blankets containing dry SAP powder, supported by beams placed throughout the roof, and sprinklers placed intermittently. Overall, soaked, this roof will only weigh about 8 pounds per square foot, which is well below the weight limits of modern roofs. Recently, we built this prototype on a doghouse. As you can see on the picture on the left, it has one support beam down the middle and a blanket shown in the lower half, containing dry SAP. Zooming in, you can see how the sprinkler system will wet the blanket and the proposed space needed. Of course, we also need to prove how effective this is.
Hi, my name is Matteo Lasseri. I'm here to explain the testing of our system. The diagram below outlines what is called the ASTM standard for the burning brands test. This is a test used to measure the fire resistance of any residential roofing system. In this test, a burning brand is placed on a metal roof and lit ablaze until it burns completely away while a steady airflow is supplied. Our test involved both a control roof with an industry standard fire resistant sheet and a custom roof with an SAP layer included beneath the metal. Here you can see the test set up in action. The roof is held at a standard angle associated with residential roofing, while the brand is burned and a fan provides steady air supply. Thermocouples provide temperature readings for both the metal roof and the bottom of the roofing deck itself. On the right, you can see what the custom roof deck looks like with SAP included beneath the metal roof. After the test, we saw that there was very little, if any, burn damage to the roofing deck where the SAP was applied. There was slight charring to the wooden supports, but no serious structural damage. The SAP itself was warm to the touch, and the cotton layer had suffered some damage, but overall was still intact. The control roof, on the other hand, was completely burned through, suffering catastrophic failure and even losing the thermocouples that were held within it. The data below shows the temperatures of both the control roof deck and the SAP roof deck, as well as the metal roof of the SAP. As you can see, not only is the SAP more effective at keeping the roof intact, but it also maintains a cool, safe temperature within the roof despite the intense wildfire conditions created by the ASTM test. For the moment, we continue to work on creating a more robust design for our product that can be scaled up to a residential level. We continue to revamp our testing and design methods in order to create a viable system that can be deployed anywhere. In the future, we plan on scoping out commercial interest in our product so that we may apply it to help wildfire-prone areas. Finally, we'd like to thank the other members of the team, without whom advancement of this project would not be possible. First, Skip Rochfort, our PI and source of guidance, and of course, Autumn Burgess and Emma Lingle, our fellow researchers who have been integral in working through the engineering challenges inherent to this concept. Finally, We'd like to acknowledge you for dedicating your time to our research and that of our colleagues within the College of Engineering. Thank you.